For decades, the standard model of cosmology has operated on a strict assumption: gravity is a patient engine. To build the immense cosmic structures we see today, gravity requires billions of years to slowly pull together and grind down raw gas and dust. This animated timeline tracks that slow evolution. Following the Big Bang, the universe entered a period known as the Cosmic Dark Ages, a hot, dense fog of hydrogen and helium without a single star. It took hundreds of millions of years for that fog to clear, and billions more for gravity to finally piece together the largest superstructures in the universe, fully formed galaxy clusters. But we can now test that timeline directly. The James Webb Space Telescope uses its massive array of infrared mirrors to peer through cosmic dust and capture photons that have been traveling since the universe was in its absolute infancy. At 10.4 billion light-years away, JWST locked onto an object called XLSSC 1212. We are seeing it exactly as it existed just 3.3 billion years after the Big Bang, an era when galaxy clusters should have barely started. Yet XLSSC 122 is already a gargantuan, highly organized supercity of galaxies. We know its massive scale because we can observe its immense gravity physically bending the light around it. By calculating exactly how much that light warps, astronomers weighed the cluster's dark matter core. It is impossibly heavy and tightly packed for that era. A structure this dense requires eons to assemble. Its existence so close to the Big Bang indicates a clear gap in our timeline for how the universe accumulated its mass. XLSSC 122 is not an isolated case. Since 2022, JWST has repeatedly found galaxies deep in the early universe that are far too massive and mature for the age we are observing them. Recently, astronomers confirmed the distance of a tiny but extraordinarily luminous galaxy called MOMZ-14. Its light was emitted just 280 million years after the Big Bang, at a point when the universe was roughly 2% of its current age. This line graph compares the chemical spectrum of MOMZ-14 on the left with that of a known ancient globular cluster on the right. Both show the exact same unusually high spikes in the ratio of nitrogen to carbon. That distinct nitrogen signature takes immense time to develop and is strictly reserved for the oldest stellar structures we know. Because MOMZ-14 possessed this chemistry almost immediately after the universe became transparent, our models for early chemical evolution cannot be accurate. This anomaly of scale extends to macromotion. This map plots the spin direction of massive numbers of galaxies across the observable universe, using vector arrows to indicate rotation. Instead of an even mix, the vectors heavily skew in one single direction. That alignment directly violates the cosmological principle. Large-scale cosmic structures are supposed to be completely random, isotropic, and evenly distributed, identical to the theoretical 50-50 split you see modeled on the right. Impossibly early mass, instant chemical maturity, and heavily aligned galactic rotation create a severe logical vacuum. Standard physical models cannot account for all three observations simultaneously. To fill that vacuum, some astrophysicists are turning to Schwarzschild cosmology. This theory proposes that our observable universe actually exists entirely within the interior of a black hole, which itself sits inside a larger, older parent universe. Under this framework, the Big Bang was not an initial explosion from a completely empty void. It was the precise moment that matter in the parent universe collapsed under its own weight to form a black hole. To understand the mechanics of that collapse, we have to look past standard relativity and incorporate Einstein-Cartan theory. This introduces a mathematical property called torsion. This animated diagram illustrates how torsion operates on a quantum level. It accounts for the intrinsic spin of particles. When matter is compressed to extreme densities inside a collapsing core, that twisting effect generates a massive repulsive force against neighboring particles. The outward pressure from that torsion eventually overpowers gravity. The inward collapse halts, and the core aggressively rebounds outward, expanding violently within the boundaries of the event horizon. Physicists call this the Big Bounce. That rapid outward recoil is exactly what we observe as cosmic expansion. We have been misidentifying a sudden, violent rebirth from a collapsing core as the absolute beginning of time. This bounce provides a direct explanation for our skewed galactic motion. If our universe was born from the core of a spinning black hole, the expanding matter naturally inherited that preferred axis of rotation. It also explains how giant clusters and complex chemistry existed just 280 million years in. Because our universe is a continuation of material from a parent universe, it started with an immense amount of inherited entropy and information, allowing those massive structures to assemble instantly. If true, this creates a biological logic for cosmology. Every black hole we observe right now could be experiencing its own big bounce, serving as a doorway to a new, fully expanding universe inside. It provides a mechanical reason for why the constants of nature seem perfectly tuned for life. Universes with stable physics generate more stars, which collapse into more black holes, allowing those specific physical laws to reproduce and dominate. The impossible galaxies caught by JWST do not mean the scientific method is failing. They provide the necessary friction required to push our understanding past a single origin point and toward a universe that is self-replicating, infinite, and deeply interconnected.